Hello, now we come to a new section of the Big Data Analytics online course. This is covering web search and text mining. There are two units here in this section, and here we come to some of the more basic information retrieval and web search issues are discussed in this first unit. As always, we're using clouds. The analytics we're running in this case are the analytics of crawling the web, the analytics of classifying queries, the analytics of classifying web pages. And all of this is collaborative because the world is collaborating to produce the web. And then the web is certainly big data, and we're solving problems here on what we sometimes call lifestyle informatics, because our lifestyle is built around the web and searching it. I'm not certain that's what is meant by lifestyle informatics back in this down here, which is probably more health-oriented meaning, but that's how I'd like to do it. So first we'll just discuss the problem, what we have to solve, and with some numbers to scope it. All right. So in this lesson, we'll first discuss the size of the search, and here we have a little bit of data on how big searches of a certain number of words are. So here we have queries rather, up to over 8 words and starting with 1 word, and you can see it's pretty uniform from 1 word to 3.5 words, but then it falls off reasonably rapidly. And if anything, there's a slight trend to longer queries. The average is around 3 words per query. This comes from 2009, but I doubt if it's changed dramatically. This is the usual problem with the web. It's not always easy to get exactly the data you want. Here we have a number of searches per day, and in 2013 it's almost 6 billion. This is Google's Google searches per day. This is 6 billion searches per day, and here's the annual number. It's too large a number for me to think about. Notice when they started, they got 10,000 searches per day. That was 1998. And it's grown pretty systematically. Maybe like 2011 to 2012 was actually only a 10% increase. This is more like a 20% increase. So it's growing. But 6 billion per day is not so trivial. And remember, we have to respond to all of these in a fraction of a second. That's 0.15 is my magic number seconds. Because your brain doesn't do much in 0.15 seconds. But it does a lot even in 1 second. So it gets very frustrated if you wait a second. If you look at when we go to the web, as we'll note, we'll have to take all these documents and divide them up into so-called tokens and terms. And that is right. A number of terms is roughly the number of different words. And here we have some measure of the number of words, which is around 1 million in the English language. So all the documents are going to be classified into what words they have and how many entries in each word. And according to this survey here in 2009, the English language crossed the 1 million word threshold. And that 1,000,000th word was the sort of interesting word, Web 2.0. And currently a new word is created every 98 minutes. And that comes from one survey. Here's another survey looking at books digitized by Google. This actually is not here. Here are the number of words, and we're up to again 1 million here from Google Books. And here's this other survey at the top here, which was also at 1 million. And here's the Oxford English Dictionary, is actually less than 500,000. It's got higher standards. Notice the total number of words in this Google digitization for English was 361 billion. and not so many in some of the other languages, but the total is around 500 billion. Big numbers, big data. Here's the size of the World Wide Web, which comes from, which is estimated in this web page here by running simple queries and finding out how many responses you get to that, and knowing from general principles what fraction of the documents would satisfy by those queries. So if you look in up to 2013, we have the size of the web for Google is about 45 billion. But then something funny happened. Something funny happened because it's changed to 15 billion. I assume some definition changed or something changed, or maybe Google's algorithm changed or something like that. But the web page didn't comment on this. Very few things these days actually go down. Here we have the size of Google's web decreased. Odd. But it's still pretty big at 15 billion. People love graphs. Computer scientists are obsessed by graphs. And so you can study the structure of the web by the graphs produced by having web pages which point to other web pages and get pointed to. So all the hyperlinks effectively define a graph. And you can look at all sorts of distributions of the number of pages with different number of in and out links and how they're connected together. And whether you can always go from one page to another page, or whether there are clumps of pages which are cut off. It'd be easy to make a clump of pages that are cut off, put up 10 web pages pointing to each other, and don't let anybody point at it by not telling them about it. So until somebody finds them, you'll definitely have an isolated subset. So here's an actual picture of the web with number of pages in various categories. This is pretty old. This is another interesting feature about this field. Some of the more interesting numbers and structures come from papers 10 to 15 years old because nobody's ever redone it, partly because the data is so big, but also because it's secret. At the beginning, it wasn't so secret because it wasn't so valuable. Now it's too valuable. So here we have a bunch of vertices with links going into them, bunch of vertices with links going out of them. We have a sort of homogeneous core with links going in and out. We have things sticking out of this thing, dendrites, 44 million here. And then we have disconnected components, 17 million. So this is the so-called bow tie structure, central core, in and out sections. And there's about a quarter of the web in the various parts, the in, the core, the out, and the rest. So we've already pointed out that the key feature of web pages is that they have links going into them and links going out of them. And here's actually again, it's an unfortunate, rather old document defining a histogram of a number of times there are links going in and links going out of documents. It does it for two types of ways of getting documents. One is the raw data, actual number of links in documents, the so-called hyperlink graph. And the other one is the user browsing graph, which comes if you actually go to web logs and follow the click-through of users and see what they do. So both of these are par laws. The par is actually around 2 for both cases. And this par law behavior is typical of many complicated things in life. Lots of complicated things fall off like par laws here, like here the number of pages with n links falls off roughly as 1 over n squared. And there is a lot of work in network and web science discussing these par laws.